Welcome to QSTI Prep Academy. So, today's explainer is basically your ultimate study buddy for mastering EPA Method 4 on your exam. I am super pumped to guide you through this material today. Look, if you're aiming to get your certification, you absolutely have to know the ins and outs of determining moisture content in stack gases. And, honestly, that's exactly what we're going to conquer right now.
All right, let's dive right in. The entire purpose of Method 4 is actually pretty simple. It's just about figuring out the exact proportion of water vapor in a stack gas stream. You might be wondering, why do we even care? Well, strictly adhering to this method is what enhances the quality of literally all the data you pull from other air pollutant sampling methods. You extract a gas sample at a constant rate, you remove the moisture, and then you determine that moisture gravimetrically. Sounds simple in theory, right? But trust me, the exam loves to test you on the nitty-gritty specifics.
We've got a lot of highly testable material on deck today. Here's our game plan for this explainer. We'll knock out the reference versus approximation methods, look at the essential gear, dig into the leak check procedures, take a quick study break down those tricky formulas, and wrap up with your final takeaways. Let's get to it.
First up, comparing the reference and approximation methods. You really need to clearly understand the difference between these two procedures for the test. So, the reference method? That's your gold standard. It's used for the highly accurate determination of moisture content, which is an absolute must when you're calculating actual emission data. The approximation method, on the flip side, is really just a quick tool. It gives you a solid estimate of percent moisture so you can dial in your isokinetic sampling rates before you run a full pollutant emission measurement. Just remember, you cannot use the approximation method for your final calculations, unless, of course, you can prove it yields results within 1% of the reference method. Moving on to essential equipment and setup. Let's take a look at the physical gear you're actually going to be hauling out into the field.
For the reference method train, it's a pretty robust, tightly controlled setup. You're going to need a heated probe, which you got to keep right around 120 degrees Celsius so you don't get any premature condensation, plus a condenser sitting in an ice bath, and a super accurate metering system that can handle flow rates up to 0.0283 cubic meters per minute. That's 1.0 CFM for those keeping track.
Now, contrast that whole rig with the approximation method train. This setup simplifies things dramatically. You'll notice it just uses two 30-milliliter midget impingers dropped in an ice bath, right before a drying tube packed with indicating-type silica gel just to protect your pump and meter. It's totally built for speed and quick estimation, generally pulling the sample at a nice constant rate of 2 liters per minute.
All right, let's talk about leak checks. This is a highly testable area. Seriously, a lot of people lose easy points on the QSTI right here, so pay close attention. Okay, so a pre-test leak check for the reference method is highly recommended. It's technically not strictly required by the baseline rule, but here's the absolute crucial point. If you do run one, your leakage rate cannot exceed 0.00057 cubic meters per minute at a 380 millimeter mercury vacuum or 4% of the average sampling rate, basically whichever is less. Make sure you memorize those numbers. 15 inches of mercury, 0.020 CFM.
Now, while the pretest is just a strong recommendation, burn this into your brain for the exam. The post-test leak check is absolutely 100% mandatory. You have to do it right at the conclusion of each run. And here's the kicker they love to test you on. You must conduct it at a vacuum equal to or greater than the highest maximum vacuum value you hit during the actual sampling run. If you mess this up, you might be stuck correcting your sample volume or even worse, voiding the entire run entirely.
Phew, okay, let's take a quick little stop right here to catch our breath. Please hit that subscribe button to keep these explainers coming. And listen, if you want to pass the QSTI exam and get that certification on the first try, send an email to qstiprepacademy@gmail.com. Drop us a line there, we've got all the tools to help you succeed.
All right, break's over. Time to get into the heavy math with Method 4 formulas. Honestly, don't let these intimidate you. I'm going to walk you through exactly how these work step by step.
First up, equation 4-1. This calculates the volume of water vapor condensed, and the math here is actually pretty elegant. You're simply taking the final weight of the condenser water and impinger, that's your VF, and subtracting the initial weight, VI. Then you just multiply that difference by the K1 constant to correct everything right back to standard conditions. And moving right along, this beautifully illustrates equation 4-2. We're doing the exact same conceptual math here, but for the silica gel. We take the final weight of the silica gel, WF, subtract the initial weight, WI, and multiply it by the K3 constant. This simply finds the volume of that stubborn remaining moisture that got caught by the desiccant at the very back end of the train.
Next is equation 4.3, which standardizes your dry gas volume. So Vm is your raw dry gas volume measured directly by the meter. You take that, multiply it by your meter calibration factor, Y, and adjust it based on the ratio of your barometric pressure, Pm, over the absolute temperature at the meter, Tm. Finally, multiply that whole thing by the K4 constant. This basically levels the playing field so all your data sits perfectly at standard conditions.
Finally, equation 4.4. This is the big one that brings it all together to give you BWS, your target moisture content proportion. You're just taking your total collected water vapor, so the condensed water plus the silica gel water, and dividing it by the total volume, which is your water vapor plus your dry gas sample volume. Basically, it's just a simple fraction of the wet volume over the total volume. Easy, right? Okay, rounding the corner to field data and final exam takeaways. Let's look at how all this prep and math translates into the actual physical data you'll be logging on the job site. When you're out there running Method 4, you've got to maintain a strict, precise log on your field data sheets. The exam will definitely expect you to know that you must pay special attention to recording the pressure differential across the orifice, that's your delta H, and the temperature of the gas leaving the condenser, or that last impinger. Monitoring that temperature is absolutely vital.
Speaking of vital, for your final takeaways, you need to burn these 3 rules into your brain for test day. First, during your run, you must keep your sampling rate within 10% of a constant rate. Second, you gotta add ice to cool that silica gel outlet well below 20 degrees Celsius, which is 68 degrees Fahrenheit. And finally, if you are dealing with a saturated gas stream, or maybe one with water droplets, you actually have to do 2 calculations, one with a psychrometric chart and one with your impinger analysis. The golden rule here, you always use the lower moisture value of the 2.
So, with the equipment setups down, those strict leak check rules memorized, and the standard formulas locked into your brain, are you ready to absolutely crush the Method 4 section of your certification exam? Review this explainer, double-check your math, and walk into that test with total confidence. You've totally got the moisture content down now, but the real question is, are you ready to tackle the complexities of Method 5 next?